nested quantifiers. So quantifiers are things like this. For all x, there exists x, something like that. You can use, you can mix this with other quantifiers together with different variables. They are called nested quantifiers. And propositional function, I told you propositional function is p of x, where x is a variable. But propositional function can have more than one variable. You can, why not just have more, 2 or 3 or more propositional functions p of x comma y with 2 variables, 2 or more. You can have many variables, not just p of x. Then we can use these quantifiers for all there exists x, for all y there exists y, like this, together in one proposition. So like this, for all x, for all y, p of x, x comma y. This means exactly what you think. For every x and for every y, p of x comma y, this proposition. And for every x, you can have mixed like this. This means for every x, there exists y such that p of x comma y is true. This means this. So you can have more, not just 2 variables or more. Okay. All right, good. So example, for all m, there exists n such that m less than n. And we have to mention the domain of this course. Z times z. This means this is for the first variable. This is for the second variable. That means m is in z, n is in z. Is this true? Think about that. For every integer m, there exists integer n such that m is less than n. True? Yes, let's solve this. It's true because you can find just one thing. For all m, so for every m, which is an integer, yeah, if there exists something, tell me. If this is m plus 1, which is of course z, then m is less than n. So we just found it. So it is true. For every m, we can find n, satisfying this. So it is true. There exists n for all m, the same domain of this course. All they are integers. Is this true or not? So I just changed their order. Do you think we can change this order without changing the truth value? Do you think it's true? Is there? So let's read this in as a sentence. There exists an integer n for which, for all m, integer m is less than n. Does that make sense to you? For there exists n. So this means there exists n satisfying this condition. is there an integer m? So this means there is, if I write this in details, there is n, at least one n, such that for all m, this. So what this means is for every m integer, m is less than n. Can you find such an integer? No. Why? This is false. Why is this false? If this is false, that means you can find a counterexample to this. What is a counterexample to this for given integer n? Yeah, n or n. Okay, doesn't matter. It can be anything. We can find many counterexamples. Just one is enough. This, if this is not true. So we found one example, counterexample to this statement. So it's going to be false. There does not exist n satisfying this. For every n, we can find a counterexample to this. So this is false. Is this okay? So it is very important that the order of the nested quantifiers does matter. So the order of quantifiers is important. You cannot change the order of this, because if you change this, the proposition can be different. The truth value can be changed. So it is very important. And you always read from left to right as we read books. There exists n such that something. Any question about these two examples? Okay. All right, let's see some examples. More examples. For all x, for all y, x greater than 0, y greater than 0 implies. Oh, I didn't say this, but this also, we can also read this as P implies Q. I will sometimes read this. If P then Q, and also P implies Q. They mean the same thing. Is this true? For all x, the domain of this course is r times r. Both are real numbers. For all real number x, and for all real number y, if x is positive and y is positive, then x plus y is positive. True? Yeah. If you add two positive numbers, real numbers, you will get a positive number always, so it's true. For all x, again, the same domain of this course, or y, then x plus y greater than 0. True or false? If for every real number x and y, every real number x, every real number y, if either x or y is positive, then their sum is positive. Is this true? False, because if it's false, you can just say one counterexample. Maybe 1, y equals minus 2. This is true, but this is not true. So it's a counterexample. So it's false. All right. More examples. Some mixed one. Okay, let's see. Let me write things. They all have this. Oh, okay. The domain of this course is R times R. Z plus times Z plus. Okay, I'm gonna give you just a bunch of examples so that you can work on right now. Try to understand their meaning and determine their truth value. So these 4 problems, I'm going to give you 2 minutes to solve this. Good question. Z. Yeah, if you understand the meaning of each statement, it should be easy. All right, shall we do these problems together? Is this true? Yeah, true. For every x, you can always find y such that x plus y equals 1, 0. Yeah, you can just say 1. Yeah, this true. And this? False. Why? If x equals 1, you cannot find y because y has to be positive integer. You cannot find an integer, positive integer, less than 1. So it's false. And 3, the third one? True. What does this mean, by the way? Yeah. So x equals 2, y equals 3, then both are greater than 1, both are integers, and their multiplication is 6. Good. True. And this? Why? Yeah, you cannot write 7 as a product of 2 integers, positive integers, greater than 1, because 7 is a prime number. It's a prime number, so it's going to be 4. You cannot find x and y. There does not exist this. Right, good. Okay, and negation, when we have negation, we can also have nested quantifiers, and then we can negate the statement. All right. Can you do this? You can do this step by step. So this means, this is actually, you don't have to worry too much about this. This is basically this form, right? Because this is a statement in X, right? If you say, then this is a propositional function for X. So it is of this form. Is that right? But we know how to move this inside. So this will be for all changes into that exist, not and this. Okay? And then you can move this again inside. This will be changes into for all y and not p of x comma 1. So this thing is equivalent to this thing. Oh yeah, I wanted to say equivalent. So when you have nested quantifiers, and if you want to negate that, you can do this by moving this negation quantifier inside one at a time. Okay. And there is also an interesting thing using this two quantifiers. Very example. Calculus. In calculus, I'm not sure if you learned this definition, epsilon delta argument. The definition, the precise definition in the calculus to define the limit of a function is like this, using epsilon delta, what's called epsilon delta argument. Okay, I'm going to use it here. This means, this definition, in calculus book, if you learn, for every delta, positive real number, there exists epsilon, also positive, such that 0 greater than x minus a less than delta epsilon implies f of x minus L less than delta. This is the precise definition in calculus. Does this sentence make sense to you? If this is your first time to see a sentence like this, it is very hard to understand this kind of thing. But the thing is, it is a very natural definition. Very good definition and natural. Even intuitive, compatible with your intuition. Although you just don't know that this is natural. Do you think this is natural? Very strange. But let me rewrite this using quantifiers. This means for every delta positive, there exists epsilon. So this is kind of nested quantifiers. We have this 0 x minus a epsilon implies this. So this is the definition of the limit in this using this logic notation. So when you learn calculus in high school, you don't use this definition, but you use a more intuitive way to define this, but not very correct, not very precise. So when we say this, usually people define this like this. If x approaches a, then f of x approaches L, right? But this is not very precise because we cannot say how x approaches A, how f of x approaches L. It's not very precise in mathematics. It's not precise enough to do mathematics using this. This is the precise definition. But looks very strange. And this is why I think we don't teach this in calculus. We don't teach this in calculus 1, I think. Did you learn this in your calculus? Now you can learn this today. All right, let me explain this a little bit more, because I think this is very good definition, very precise in mathematics. But it can be very confusing. Okay, right. Let me just read this sentence again. There exists, for every delta, positive delta, there exists epsilon such that this means x is close to A. If one way to think of this is if x is close enough to A, here it means then f of x is close to L, as we wish. Basically, the idea is this. You want this limit to be L. That means f of x is very, very close to L if x is close to A. That's basically the idea. But we want to make this as a precise definition using epsilon delta. That is how we do this. But the thing is, this is chosen arbitrarily. And for any choice of delta, no matter how you want this to be close, because if delta is very small, this will be very close to L. But you don't decide this L, this delta. For every L, every delta, it will be, if x is close enough, f of x is close to L, as no matter how you want it to be. Still very confused, so let me explain this using this archery thing. I think this can be helpful. Suppose that you are the archery coach for this national archery team. You want to hire a candidate, all right? You want to hire the best candidate possible. Suppose you have a candidate number 1 who claims like this. So you know archery, 양궁, if you want. There are some target here, and this archer sends an arrow, and this archer wants to send this arrow as close possible to the center, right? That's what archery is. What archery is. So this the first candidate says, I can put this arrow inside the radius 1 centimeter from the center. The first person says like this. I can always send my arrow inside this circle of this radius 1 from the center. Yeah, pretty impressive, but let's see. The second person says, okay, I can put an arrow or shoot an arrow inside say circle that I draw. So that means this guy, he draws a circle, and then he can shoot this arrow inside this circle. But this circle was chosen by himself. 3, I can put or shoot an arrow inside a circle drawn by anyone. All right? Now, you are the coach. You have to hire one of these. Which one do you want to hire? One? If you want to hire one, raise your hand. Two, I'm going to hire the second person. I'm going to hire the third person. Raise your hand if you think you want to hire a third person. Yeah, many of you think third person is the best one. Why? If you think that the third person is the best, then you have the intuition which tells you that this is a good definition. So no matter how you draw your circle, but actually I missed something, but not always. There is a condition. There is a condition here. Okay, let's say that it doesn't have any condition. If I focus enough, because even the best archer cannot shoot in the center if he is not prepared. If I do my best, I can shoot it at the center of the circle that you draw. This condition is important because, but even though you have this condition, you would choose a third person, right? Yeah. This is that thing. If I focus enough, I can shoot the arrow inside the circle. That means this guy is very good archer. No matter how you choose, that means every choice of the circle, I can do that. This is why we don't define there exists alpha. We don't define like this. If you define like this, it's not going to be continuous at all in your definition. It does not match with your intuition. But if you have for all delta, for all there exists epsilon, for every circle, for any circle that anyone draws, if you focus enough, your arrow will go inside the circle. This is the philosophy of the epsilon delta argument, which is very, in this way you can feel it's more natural than before, right? In this way, this is very precise. You can really do mathematics in analysis using this. Okay. So this is one example that nested quantifiers are used in real math or in real life. There is one more thing. Finally, let me tell you one more thing. This is also a very common phrase in a movie teaser. No matter what you imagine, you probably heard this. This movie will show you more than that, right? This is essentially the same structure as the previous one. So let's say this means the movie is very good. It is very good. No matter what you imagine, it will show you more than that. So let's say X is imagination. And Y is, say, a scene in the movie. And say P of X comma Y, this scene Y is more than the imagination. Then what this sentence says is that for every imagination, there exists a scene which is better than imagination, right? So, this is very common phrase in real life. You would probably use this kind of thing in your real life. So these are important concepts. You can use this in real life.